Alright, so next I want to talk about coordinate systems in some more detail. So before I talked about how you could pick an origin and a direction for the positive y and positive x directions. So there are cases where you would want to use a more complicated coordinate system, and I'm going to go through two examples here. One example is when you have a box or some other object on a ramp or a slope. First, I'll show you what happens if you try to use the normal coordinate system of up being positive in the y direction and to the right being positive in the x direction. So we can draw a free body diagram, and we can split up the normal force into its components, and then apply Newton's second law. And what we find is that we have these two components to the acceleration, and both of those will not be zero. It turns out that this is solvable, but it gets complicated, especially in terms of figuring out what the magnitude of the normal force is. So instead, we can change the coordinate system. Instead of using x and y, I'm going to label these the parallel and the perpendicular direction to make it clear about what is going on. So one of the axes is going to be perpendicular to the slope, and one axis will be parallel to the slope. And what this means now is that the normal force is along one of the axes. We also know for a fact that the acceleration will only be along the parallel direction, because this box is not going to fall through the slope, and I guess I will tell you that the box is not going to jump up off of the slope. So it will stay parallel to the slope. That does mean that the force of gravity is now needs to be divided up into components. But we can still draw a free body diagram, and we can write out Newton's second law, setting the perpendicular acceleration to 0. And from that, we can now divide up the force of gravity into its components and solve for the acceleration. The math ends up much, much simpler when we use this coordinate system. Another example where we want to pick our coordinate system very carefully is when we talk about two masses on a pulley and that are connected by something like a string or a rope. So this is a setup that is called an Atwood machine. In principle, it's quite simple. We have two free body diagrams because we have two masses, and in both of them we have two forces. There's the force of tension that's up, and the force of gravity for that mass that's pointing down. We might be tempted to use the same coordinate system for both. For example, we might want to say that up is positive for both of them. But there is something we know about their motion. We know that if one box accelerates upwards, the other box must accelerate downwards. Because we're dealing with two separate objects in this case, when we're doing our math, we want to make as many variables the same as possible so that we can combine the equations we get more easily. So we would like the acceleration to be the same for both of them. And the magnitude is already the same because the rope would have to stretch or compress for them to have different acceleration, but the direction is different. But what we can do is pick two different coordinate systems for each box. So for the first box, we can say that up is positive. For the second box, we say that down is positive. And when we do this, the accelerations are exactly equal. They have the same sign and the same magnitude. If we didn't do this, if we said that up was positive for both, then the acceleration of box 1 would be equal to the negative of box 2. And again, that's something you can do in your math, it just makes it more complicated. So picking the coordinate system carefully can simplify your math a lot. And in the worksheets, you will go through a problem for each of these cases to see exactly how to use these coordinate systems.